We now look at what are called maximal planar graphs. Okay? So a planar graph is given to you, let's say. Okay. Now, one question that you can ask is that can I add any more edges to this graph? Right? Any edges between non-adjacent vertices, right? So that the graph remains planar. So if I can do that, then the graph is not maximal, right? So I can still add more edges. If that is not possible, then we say the graph is maximal planar. So let us look at one example, right? So here the graphs given below, right, all are maximal planar, right? Of course, the single edge, you cannot add any more edge. It is maximal planar. And if you take the triangle, right, which is a complete graph again, you cannot add anymore. Therefore, that is also maximal planar. Similarly, K4 is maximal planar because it has all the possible edges and it is planar. And now here you have another graph, which is a planar graph, right? I claim that this is maximal planar. You cannot add any more edges. So I want you to think about why this graph is maximal, right? You cannot add any more edges to make it, to still keep it planar. Right? On the other hand, let us take another graph, right? Let us say this. So this graph is not maximal planar, right? Because I can add more edges to it, like this edge. Can I add any more edges? I can still add more edges, and to make it keep still planar. For example, I can add this edge. Now, is it maximal planar? I say that it is not. I can still add more edges. For example, I can add this edge, right? Or I could have added, for example, this one. So it is also still maximal. It's also planar. Now, can I add any more edges? I claim that I cannot add any more edges, so that the graph will still be planar. If I add any other edge, for example, between these two, right, or any other non-adjacent vertices, you will see that the graph is not planar anymore. So this has become maximal planar. So what is this property that makes it maximal planar? Can you think about this? But our definition says that if you cannot add any more new edges to make the graph or keep the graph planar, then the graph is maximal planar. So as a homework, prove that if a graph on at least 3 vertices is maximal planar, then every face boundary is a 3 cycle. So this is a nice property. If the graph is maximal planar, you take any embedding of this graph, you will see that every face boundary will be a 3 cycle. Now, if every face is a 3 cycle, you cannot add any edges in this cycle, right? Because any 3 are adjacent there. And if you do anything else, you will see that that is not going to be keeping the planarity. On the other hand, if a face boundary is not a 3 cycle, you can find 2 non-adjacent vertices, and within that face you can draw a curve connecting these two. Therefore, the graph will be still planar. Right? So this is the idea. Second question is to prove using the property that we just showed, to show that G is maximal planar with at least 3 vertices. Then it has exactly 3n minus 6 edges. Okay, so a planar graph which is maximal planar, has exactly 3n minus 6 edges. Now, if you want to prove the earlier result that a planar graph has at most 3n minus 6 edges, you can also first start with the graph G, right? Add as many edges as you can to make the graph maximal planar, and then show that now every face boundary is a triangle, and show that using this you will be able to do a counting where the number of edges is actually equal to 3n minus 6. And therefore, since I added more edges, right, without adding any vertices, I added more edges to make a maximal planar graph, and you still have only 3n minus 6, you will see that any planar graph that we started with has less than or equal to 3n minus 6 edges. Right? So this is another way to prove it. Now, here is another question. Use Jordan-Karp theorem to prove that K5 is not planar. Okay. So again, it is a very nice exercise if you can do it yourself. So think about this. Can you use Jordan-Karp theorem alone to prove K5 is not planar without using the Euler identity? So here I present a solution. So what does the Jordan-Karp theorem say? It says that a simple closed curve separates the plane to two disjoint open sets. Right? One is the interior part and the exterior part. So how do you use this to prove the non-planarity of K5? So here let us see. So what we do is that we name the vertices as V1, V2, etc., V5. Okay? Now we know that the graph is complete, which means that between any two vertices there is an edge. So if you take V1, V2, V3, they form a triangle, right? There is a complete subgraph, therefore they form a triangle. So V1 is connected to V2 and V3. Now, this forms a closed curve because you have this 3 cycle. Now, this 3 cycle divides the region, right, the plane into two parts. One is the interior part, one is the exterior. Now, since you are looking for an embedding of K5, you have to add the other vertices, right? So you want to place the vertex V4 on the plane. Of course, the only possible places where you can place this are either inside or outside. Both are identical, right? So we will not worry about this. We will see that one of the cases is sufficient, right? By symmetry, we will assume that the vertex V4 is kept inside. So we can assume that the fourth vertex is either inside or outside, so it can be inside, right? So you have the interior and exterior. So look at the interior part. We will assume that V4 is sitting in the interior, right? So we are going to keep V4 in the interior. Now, if you keep V4 in the interior, now V4 is connected to V1, V2, and V3 because the graph is complete. So we will get V4 connected to V1, V4 connected to V2, and V4 connected to V3. Now, this again divides the internal region of the triangle, right, that we started with, into three sub-regions, right? You have these three different phases. So you get the three different phases. Each one is a cycle, right? Boundary is a cycle, which is V1, V4, V2, and back to V1. Or you have V2, V4, then V3 and V2. Or you have V3, V4, V1 and V2, V3. V3, V4, V1 and V3. It's not V2. Right? So, so we have these three sub-regions, right? So these are regions of. Now the question is that where are you going to keep the vertex B5, right? Suppose you take the vertex V5. We know that V5 is adjacent to V1, V2, and V3, right? It's adjacent to all other vertices. So in particular, it is adjacent to V1, V2, and V3. Now the only connected area which is having all these vertices, right, is precisely the exterior face. So therefore, our last vertex must be in the exterior face, right? The only place where I can keep V5 is the exterior face because it must be connected to V1, V3, and V2, all three. But then, if you keep it in the exterior of C, V4 is in the interior of C, right? And therefore, the curve C, which is V1, V2, V3 cycle, that curve divides the region into two, right? Interior and exterior. And therefore, any path from V5 to V4 must necessarily cross the curve that we have just created, right? V1, V2, V3. But this is not possible, right? So therefore, the edge must cross the curve. So therefore, the embedding is not planar. So hence, you can just use Jordan curve theorem to prove this. So similarly, I want you to do as a homework to prove K33 is not planar by again using Jordan curve theorem. Okay, so think about this. Now, there are many other things one can do with these things, but for the time being, I want to look at a different topic, which is very interesting and very powerful. Okay. This is called the discharging method. Now, before going into the discharging method, let me tell you a little bit of history. So this method was developed by Heast in, I think, if I remember correctly, in 1904. Now, this result has been used very less for like maybe around 50 or 60 years. And after this, or maybe 70 years, after this, this was used in a very, very famous paper by Ira Appel and Haken, Wolfgang Haken and Ira Appel, who proved in 1976 a very long-standing conjecture called four-color conjecture. Okay? So this four-color conjecture came from the following question. There was, in I think it was in probably 1850 or something, right? 1850, 51, if I remember correctly, right? Francis Guthrie, right? He was a map maker. So he asked the following question, right? Suppose you have a map of a country. Let's say we will assume for simplicity that all our countries are connected region. That you don't have several parts in the world which are a part of the same country, which is actually true, but we will assume that is not the case. Now, if you have connected regions and you want to color the map of the world map, let's say, giving different colors for different countries, right? Not necessarily different colors. You want to different colors for adjacent countries, so that you will see, immediately, like these two are different countries, or what is the border, etc. Now, of course, one can say that okay, use a different color for each country, right? This is definitely a possibility. But there are two issues with this, right? One is that if the number of colors increases, then the difficulty of resolution, right? Looking at a color and differentiating becomes more and more. Right? When the number of countries is high, you will have to use different shades of colors which are close to each other, so that many people may not be able to distinguish between the small difference in the colors. So we cannot use too many different colors. So it is always better to use as low as the number of colors possible, right? If you use the minimum number of colors, like let's say just 2 or 3, then it's very easy, right? You can just use like red, blue, green, or some very contrasting colors, so that it's very pleasing and immediately clear what is the borders of the countries. So you want to, so one natural question for a map maker is to see what is the minimum number of colors with which you can do the coloring. So what this map maker observed is that he can do with 4 colors for all the cases that he has seen, right? Now he wanted to ask, is it always possible, right? No matter how the country's borders are, can you always say that we can color the graph with at most 4 colors? Now, this question was asked to some mathematician friend, and then he kept it at a log. He emailed to some famous mathematicians who looked at it and then replied that he is not clear. He will look into it and then ask others. And this problem has been in circulation, and many people have started looking at it. And there were several attempts to prove this. So after 125 years, okay, in 1976, finally it was proved by Appel and Haken. These two people proved this method, proved this result using a technique called the discharging method. Now, this discharging method proof became controversial because the number of cases in this was too huge. So they had to use computer help. They had to write some algorithm to verify whether the result is correct. So the computer basically verified the calculations. And therefore, many mathematicians said that this result is not acceptable. Now, what is the reason for them to say this? This is this has nothing to do with the persons or that it has been used with computers, but the computers has an inherent issue that a computer is an electronic device which usually in the manufacture people see that after some time there could be some bugs. Now there are certain kinds of bugs which may be triggered only in the execution of certain specific sequences of instructions. Now there are several such bugs which appears in computer science. Everything will work fine only if you give a specific sequence of instructions, then the computer produces or the algorithm produces a wrong result. Now the mathematicians ask, okay, what happens if this particular sequence of instructions was the algorithm that you use to solve the cases of the planar, the proof of the four-color theorem. So therefore, they said that okay, we don't want to take it for granted, but of course, without any other proof, we have to take it because this is a serious attempt, and we cannot find any problems with it other than the fact that it is using computers. So then, after some time, other people wanted to see if they can come up with a different set of proofs, and there are very famous mathematicians, 4 of them in fact, Robertson, Seymour, Robin Thomas, and one more person, Steele and Thomas. Yeah. So these 4 people try to come up with a different proof without using the help of computers. So they came up with a very different idea. They simplified the arguments of Appel and Haken. they came up with several things, and finally they said that okay, they also need to use a discharging method, and they also had to use the help of computers. So after, this was in 1996, if I remember correctly, and then there were a couple of more attempts, and each of the attempts so far to prove this always use the discharging method eventually, and also always use the help of computers to do some computation. So if you can come up with a proof without using computers, that would be great. Now the question is about discharging method. Now the question is the discharging method so powerful that it is required to prove four-color theorem? We don't know. We so far all the results all the proofs have used discharging method, but this method is very powerful in the sense that it can be used to come up with several structural properties of classes of graphs, including planar graphs. And not all applications of this method requires the help of computer. So we are going to see some simple examples and study this method. And of course, we don't have time to look at the proof of the four-color theorem, but we will learn the technique that is used to prove the four-color theorem. So to look at the question again, let us look at this map of India. Okay, so we look at the map of India, and we want to color the map using the minimum number of colors. So the aim is to try to use as least colors as possible, and then I observe that I have to use at least 4 colors. So why is that? Let us look at the current map of India, and then look at the cases why we require 4 different colors. Why we cannot do with 3 colors. So we will start with the assumption that we start the attempt by using only 3 colors. So we will start with, let's say, one of the states, Madhya Pradesh. Okay? So Madhya Pradesh definitely needs 1 color. So I will start by giving it the color green. Now, since adjacent states should get different colors, now immediately I see that Uttar Pradesh is adjacent to Madhya Pradesh, right? So therefore, Madhya Pradesh must get a different color. So other than green, I have to give some other color. So let's say that I give blue. Okay. Now, we observe that Rajasthan is bordering both Madhya Pradesh and Uttar Pradesh. So since it is bordering both of these, I cannot use either blue or green. Right? So I use red to give Rajasthan. Now when I go to Gujarat, I see that okay, Gujarat can be colored blue because it is adjacent to, of course, Rajasthan and Madhya Pradesh. So I cannot give red or green, but I can use blue. So I will give blue to Gujarat. Then I come to Maharashtra. So Maharashtra is adjacent to both Madhya Pradesh and Gujarat. So I have to use a color other than green and blue. So I give red. Then I come to okay, so this is not the current map, I think. This is a map before the division of Telangana and Andhra Pradesh, right? So let us say that this was not green. Okay, so then I come to Telangana, right? So Telangana is can be colored with let's say green, right, or blue actually, because we are assuming that we have not colored anything else. So let us say that I color Telangana with green. Now, no matter what I color, no, I don't have to go to Telangana, right? Because yeah. So now let us look at this. So now I look at this is, I think, Chhattisgarh, right? So let us look at Chhattisgarh. Now Chhattisgarh is adjacent to both Madhya Pradesh, Maharashtra, and also to Uttar Pradesh. So therefore, since I had been forced to give, different colors to Madhya Pradesh, Uttar Pradesh, and Maharashtra, right? Because all these colors were forced. I started with one color, green. Then I had to use a different color, so I used blue. I had to use a third color, so I had to use red. Now I don't have a choice to give, if I am using only three colors, I don't have a choice to give anything other than blue to Gujarat. And similarly, I did not have a choice to give anything other than red to Maharashtra if I am using only three colors. And therefore, I had been forced to give three different colors to Uttar Pradesh, Madhya Pradesh, and Maharashtra. Now, Chhattisgarh is adjacent to all these three, neighboring all these three. So, therefore, I cannot give any of these three colors to Chhattisgarh. So, I have to use a different color, let's say brown. Right? So, this is the argument to see that we need four colors to give the colors to the districts, the states of India, right? At least four. Now the claim is that four is sufficient, right? Why is that? So now one can immediately convert this into a graph theory question, as you can probably see now, right? Just put vertices at each state, right? Center of each state. Then whenever two states have a common border line, you put an edge connecting them. So that defines the graph, right? And this tells us how to convert the map coloring problem to a graph coloring problem, right? So now I have to color the vertices, right? If I give a vertex a color, it cannot get any adjacent vertices cannot get any that color. So therefore, if I have a coloring of the map, I have a coloring of the graph, and if I have a coloring of the graph, vertices of the graph, I have a coloring of the map also. Okay? So I have converted the map coloring problem to a vertex coloring problem, right? Sorry. So I have converted into a vertex coloring problem. So now one can show that converting this kind of maps to graphs, right? If assuming that the regions that we are looking at are all connected, single regions, right? Then you can show that the graph that you obtain are planar graphs, right? In fact, there are more planar graphs that you can obtain. Like there are all the graphs that you obtain from the map by doing this are planar graphs, assuming that maps are connected regions. And but of course there are other planar graphs which are not obtainable this way also. But we now prove that for every planar graph we can do with four colors. So therefore it says that maps can also be colored with four colors. So that is the idea of the that is the idea of converting this to a graph problem. So now people were looking at solving this question on the graph coloring, right? Not just map coloring, also graph coloring. So this graph coloring has been active for like almost 125 years, and before it was finally proved. So there were some very interesting attempts to prove this, and some of them stood, people believed it to be correct for almost 11 years, and before somebody found there is a problem in the proof. So it's always a good idea to look carefully before accepting any any even accepted within quotes results as true, right? Because people can of course miss some important points and then think that it is correct. But anyway, let us continue. So the four-color conjecture was that any planar graph can be properly vertex colored with at most four colors. So this was open from 1952 to 1976. I think I mentioned 1852 to 1976. I mentioned as 1851. I think it was 1852. Now, So if you recall, the proper coloring of a graph is basically assigning colors to the vertices such that adjacent vertices get different colors. So here is an example of a proper forecoloring of a planar graph. So here you have a planar graph and you have colored with 4 colors. And can you show that 4 colors are necessary, right? Or you cannot do with less colors, or if you can actually do with less colors, show that also, right? So now uh, so this is something that we already mentioned, that the first proof of this was proved by Appel and Haken in 1976. Used the discharging method and needs a computer assistance. Now this original paper was around around 2000 page, because of the different computations and all the calculations that were there. Then the second proof came in 1996. Robertson, Seymour, Steele, and Thomas, and they also used discharging method, and they also required computer assistance, but they reduced the number of pages to something like 600 or something, if I remember. Then there were other attempts, but all the non-proofs, as we mentioned before, use discharging method and computer help so far. So if you can come up with a proof without using computer help, you will be a big name in computer science. So let us look at a trivial example to study the discharging method.